Hello friends, welcome back to my channel again. I am Bijay Lohar here. Today in this session we are going to discuss about a very important data link layer protocol called spanning tree protocol or STP. So if you are preparing for the CCNA, this session will definitely help you to understand the entire process of a spanning tree protocol. So let's proceed with the topic. As I said, that spanning tree protocol is a data link layer protocol defined by 802.1d standard of IEEE. So it's a standard protocol, not the proprietary one, and the main purpose of a spanning tree protocol is to ensure a loop-free switch network when we have redundant link between the switches. We all know that it's a good practice to have redundant link for the failover situation, but what problem may occur if we use redundant link without spanning tree protocol? So let's see some cases with the broadcast traffic. As we know that whenever a switch gets a broadcast message, switch is going to forward that traffic from all exit interface except the interface it has received. So what will happen with that? To understand this thing, let's have a basic topology. As you can see here, we have two switches connected with each other using redundant link. So what will happen if this switch gets a broadcast message? This switch is going to forward that traffic from all exit interface. So the traffic is moving through this interface to this switch, and now because your traffic is a broadcast traffic, now this switch is going to do the same thing what switch A did earlier. So this switch is going to forward that traffic from all exit interface. So the same traffic switch A is getting from another interface, and this cyclic process will go on, and such environment of network is called looped network. So this is the first case can happen in our redundant link without spanning tree protocol. Now see the second one. As you can see here, we have three switches connected with each other. So we have redundant link to reach a particular destination. But what will happen if this switch gets a broadcast message? This switch is going to forward that traffic from this interface as well as from this interface. And as this switch gets that frame from this switch is going to update its MAC table that I am getting this particular frame from this switch using this interface. But after a few time, this switch is getting same frame from this switch using this interface. So now it has to update its MAC table again. And this process will continue for all switches because they are getting same frame from different interface. So the problem is unstable MAC table. So this is the second case can happen without a spanning tree protocol. Now let's see the third one. As you can see here, we have three switches connected with each other using redundant link. So to reach a particular destination, we have multiple routes. But what will happen if this system generates a broadcast traffic for particular this computer? This switch is going to forward that traffic from this interface as well as from this interface. Now this switch is going to deliver that frame to the destination. But after few time, this switch is getting same frame from another switch using another interface. So now this switch has to deliver this frame to this computer again. But at this time, the frame is a duplicate frame. So this is the third problem, that is duplicate framing can occur without spanning tree protocol in our redundant link. So this all broadcast traffic problem can occur in our redundant link network without spanning tree protocol. And to overcome this problem, we need STP. As we discussed earlier, 802.1d is the base spanning tree protocol, and by default all catalyst switch ports are enabled with STP. There are several improved versions of a spanning tree protocol has been introduced over the year. As you can see here, the first one is STP 802.1d, that is the standard or original version of a spanning tree protocol, and the second one is PVSTP plus, that is per VLAN spanning tree protocol plus. Third one is RSTP, that is rapid spanning tree protocol, and the fourth one is rapid per VLAN spanning tree protocol plus. Basically, STP avoid looped broadcast traffic by changing some interface to forwarding state and some interface to blocking state. But for deciding which interface will be in forwarding state and which will be in blocking state, we'll have to understand the process of spanning tree protocol. So this is the entire process of a spanning tree protocol, and the first process is electing a root bridge. So one among the switch will be the root bridge. Whenever multiple switches connect with each other, they all assume that they are most suitable for being a root bridge. But to select a particular switch as a root bridge, they all participate in an election process by sharing their BPDU information. BPDU is basically Bridge Protocol Data Unit, which contains bridge ID, priority, MAC address, and root cost or port cost. So the condition of electing a root bridge is the bridge or switch with the less priority will be the root bridge, and by default all switches having 32,768 as their priority, and +1 is the VLAN, so the priority is 32,769. So let's verify which switch must be the root bridge. We'll have to verify the priority. We have the condition that the most less priority bridge will be our root bridge. So verify the priority, enable show spanning tree, and this field particularly defines the information about this switch. So the priority of this switch is 32,769. Okay, now check this one, enable show spanning tree. The priority of this particular switch is 32,769 again. Now the third one, enable show spanning tree. And what we see here, the priority of this switch is also 32,769. So they all switch is having 32,769 as their priority. So the first condition of electing root bridge, that is less priority bridge will be the root bridge, is tying. So what next STP is going to do, that it is going to compare the MAC address of each bridge. So the smaller MAC ID will be the root bridge. So the switch with the most smaller MAC ID will be the root bridge. So now we'll have to verify the MAC address. As we used earlier, show a spanning tree command, just below your priority there is your MAC address. So the MAC address of this particular switch is starting from 00E0. Okay, I have already copied there. Okay, now check this one. So the MAC address of this particular switch is starting from 0001. Okay, here it is. And now for this one, the MAC address of this switch is starting from 0007. So if we compare the MAC ID of each switch, this is the smaller MAC ID among all these switches. So this switch must be the root bridge. We can verify it. As you can see here, we used command show spanning tree earlier. So now at this point you can see that this bridge is the root bridge. So the root bridge is selected by comparing MAC ID, and the smaller MAC ID starting from 0001. So this switch is our root bridge. Okay, so root bridge is selected. What next we have to do here? Let's see what is the second process of a spanning tree protocol. Once the root bridge is selected, the second process will be change all interface of root bridge into forwarding state. So the second step is very easy, that once the root bridge is selected, all the interface of root bridge will be in forwarding state. Now proceed with the third process. And the third process of a spanning tree protocol is defining root port for the non-root bridges. So once the root bridge is selected, all other switch will be the non-root switches or non-root bridges, and they will have to select a particular port as their root port. Basically, root port are the shortest, less cost route to reach our root bridge. So as you can see here, we have this route as the most shortest route to reach our root bridge. So this is our root port. But if we have multiple route to reach root bridge, we'll have to compare the cost of each route, and the most less cost route will be our root port. So to understand the cost of a route, we'll have to remember this table, as you can see here, because the cost of a route directly depends on the speed of your interface. So, if your interface speed is 4 Mbps, the cost of that route will be 250. If the interface speed is 10 Mbps, your cost will be 100. If your interface is 100 Mbps, your cost of that route will be 19. And if your interface is 1 Gbps, the cost of route will be 4. And if your interface is 10 Gbps, the cost of that route will be 2. So, if we are using fast Ethernet, so our cost is 19. So, if we compare the cost, we can see here is only 19 as a cost in this route, but if we try this route, we are getting 19 plus 19 equal to 38 as the cost. So, according to the cost, this route is the route port as well as the most shortest route to reach our route bridge. Okay. Once the route port is selected, what next we have to do here? We'll have to see what process will continue with the spanning tree protocol, and that is defining a designated port. So, once the route port is selected, the second process will be for selecting a designated port. So, basically designated port are the alternative best less cost route to reach our route bridge. And if we have multiple links to reach our route bridge, we'll have to compare the following things. As we discussed earlier, during selecting a route port, the first thing what we'll compare is cost, and the minimum cost of a route will be selected as a designated port just after your route port. So, the second one is if the multiple route is having same cost, the second thing which is going to compare, that is bridge ID or priority. So, the bridge with the less priority will be selected as a designated port. And again, if the cost and priority both is same for the multiple route, the switch with the less physical port will be selected as a designated port. So, this thing will be compared during selecting a designated port. So, once the designated port is selected, now the final stage will be blocking all other interface. So, this is the entire process of a spanning tree protocol. But a spanning tree keep watching each link by sharing BPDU information. During the selection of route bridge, they all used to share their BPDU information, but once the route bridge is selected, now only route bridge is going to share their BPDU information. So, if a link goes down, STP has to reconverge all the network link over the topology. To understand the reconvergence of a spanning tree protocol, we'll have to understand the timer of a spanning tree protocol. So, this is the spanning tree protocol timer, and the first one is hello timer, and by default it is of 2 seconds, where the route bridge used to share its BPDU information with other switch, and it do not get reply for hello request. Now the max edge period will be there. So, if a link goes down, route bridge is not going to receive any hello reply. So, the max edge period will be started, and that is of 20 seconds. So, route bridge is waiting for 20 seconds for reply with the next switch. But even after 20 seconds, if route bridge do not get any reply, now the forward delay period will be started. Basically, forward delay period is the situation of listening and learning of our interface, and that is of 15 seconds. So, total forward delay period will be of 30 seconds. And during this timer, switch interface has to change in different state. So, this is the state of our interface working with the spanning tree protocol, and the first one is disabled, which defines an administratively down interface. Blocking, the second one is blocking, which defines the interface is blocking traffic. Listening, in this state, interface is listening BPDU but not learning MAC address. Now, the fourth state is learning state, where the interface is learning MAC address but not forwarding traffic. And the fifth one is forwarding state, which defines the interface like normal, forwarding and receiving traffic. So guys, this is the base spanning tree protocol. But one more thing I'd like to point you that if a link goes down in a spanning tree protocol, it's take about 30 or 50 seconds. 30 in case your secondary link goes down, but it will take 50 seconds if your primary link goes down. If you disconnect this one, it will take 50 seconds to reconverge, because now this switch is waiting for max's timer, and even after 20 seconds, if this switch do not get reply, it is going to start listening and learning situation, and that will be of 30 seconds. So total period to come back this link, it will require 50 seconds. But you may have noticed that whenever we connect a link to a particular switch, it takes exact 30 seconds because there is no max's timer. So if you are working for the video or voice traffic network where not even a single second is compromisable, we'll have to proceed for the improved version of a spanning tree protocol. We'll discuss about this improved version of a spanning tree protocol in our other session. I hope you guys like this video. If so, please do subscribe with our channel. Till next one, bye bye.